Hello, in this video I am going to explain elastic properties of materials which comes under module 2 of VTU syllabus, and here I am going to concentrate on neutral axis and bending moment of a beam. So if you look at this picture, so you can look at a beam here which is uniform from one end to another end and whose length is very large when compared to other dimensions. So here we are considering a wooden scale, rectangular in nature, whose length is very much greater when compared to its breadth and thickness. And in this picture we can see three layers. The top layer is AB, the middle layer is CD, and the bottom layer is EF. When we bend the beam, so the deformation is going to happen as shown in the second picture. So the top layer, that is AB, undergo elongation and elongated to A dash B dash, whereas the bottom layer EF undergo contraction and contracted to E dash F dash, whereas the middle layer CD will not undergo any deformation. So that's what the picture explains here. So in the next slide, you can look at the theoretical part. So it is a homogeneous body of uniform cross section whose length is large compared to its other dimensions. That is what is called beam. So consider a beam whose one end is fixed and a load is attached to the free end or other end. The beam bends. A filament such as AB of an upper layer will be elongated to A dash B dash, and the beam, that is the layer such as EF of lower layer, will be contracted to E dash F dash. But there will be always a particular layer which will not undergo any change in its length. That is what is called CD. Such a layer is called neutral surface, and the corresponding axis is considered as neutral axis. So here the layer CD is treated as neutral axis or neutral layer that will not undergo any deformation because of applying load. So in the next slide I am going to explain the expression for bending moment of a beam. So here is a picture. The beam is bended because of applying load, and the layer such as AB gets elongated to A dash B dash, and the layer such as EF gets contracted to E dash F dash, and the middle layer CD will not undergo any deformation. And here let theta be the common angle subtended by the layers at the common center O of the circles. So here the shape of the filaments are in circular path. So let us consider R be the radius of the circle of which neutral surface forms a part. So here capital R is the radius of the filament CD forms a part of a circle. So because of this, the length CD will be considered as capital R into theta. So here R is the distance of CD from common center O. Next, so the change in length of the filament, that is AB, will be considered as A dash B dash minus AB. So the upper filament whose change in length will be equal to A dash B dash minus AB. But it is observed that AB is equal to CD, that will be equal to R theta. Also A dash B dash will be equal to capital R plus small r into theta, and small r is the distance between the successive layers. Therefore the change in length will be equal to capital R plus small r into theta minus capital R into theta. So here capital R theta cancels, so it will be equal to small r into theta. And the original length will be equal to AB, that will be equal to capital R into theta. Therefore, linear strain is equal to change in length divided by original length, that is small r into theta divided by capital R into theta. So theta cancels here, that will be equal to small r by capital R. Next, the Young's modulus is given by capital Y, which is equal to longitudinal stress by linear strain. That is the formula for Young's modulus. Therefore, the longitudinal stress will be equal to Young's modulus Y into linear strain. But we already calculated linear strain is equal to small r by capital R. So substitute the value there. So longitudinal stress is equal to capital Y into small r by capital R. But it is observed that stress is nothing but force for area. Therefore, in place of longitudinal stress, substitute F by A. So F by A is equal to Y into small r by capital R. So finally, the value of F is equal to YAR by capital R. That is what the force. Now, the moment of this force F about the neutral axis will be equal to force into perpendicular distance. So that is nothing but F into small r, or that is equal to YAR square by capital R. And the moment of this force acting on the entire beam is given by summation of YAR square by capital R. That is equal to Y by R summation of AR square. But it is observed that summation of AR square is equal to Ig, that is the geometric moment of inertia. Therefore, moment of the force is equal to Y by R into Ig. Or bending moment is equal to Y by R into Ig. So here we can discuss about two cases, that is bending moment of the beam by considering a rectangular cross section. So if you consider a beam of rectangular cross section, the bending moment is equal to Y by R into BDQ by 12. So here the value of Ig is equal to BDQ by 12 applicable to a beam of rectangular cross section. And here B and D are the breadth and thickness of the beam respectively. And if you consider a beam of circular cross section of radius rho, then the bending moment is equal to Y by R into pi rho to the power of 4 by 4. So in place of Ig, we are substituting pi rho to the power of 4 by 4. So rho is nothing but the radius of the beam. So this is what about bending moment of a beam by considering a beam of rectangular cross section and a beam of circular cross section. Thank you.